Hello and welcome to this video lesson. We're going to be going over the practice test for Unit 5A, and we'll start taking a look at it. The answers are already here, but what I'm going to be explaining in this video is why are these the answers? Why is 6 squared 36, and so on and so forth. So let's go ahead and start with number 1. As I said, 6 squared is 36, but why? Because an exponential expression, it's not 6 times 2. It's the most common incorrect answers. People will say that this is 12 because 6 times 2 is 12, right? But no, that's not correct. The definition is take this many of those and multiply them together. So this is 6 times 6. There's 2 6's, multiply them together. That's 36. Likewise, this says take 3 of those and multiply them together. And 11 times 11 times 11 is 1,331. Those are the definitions. These are perfect squares and cubes. What about number 3? The radical symbol. If you don't see a number there, that was terrible, let me fix that. If you don't see a number here, like for instance we see a 3 there, but if you don't see a number, then it's implied that there's a 2 here. It's implied that this is a square root, which is asking the question, what number if I take 2 of them? That's what that little number means, It's not an exponent, it's a root. What number if I take 2 of them and multiply them together? I get, in this case, 144. And this has 2 different answers. This could be 12 squared is 144, and also negative 12 squared. In other words, 12 times 12 is 144, and negative 12 times negative 12 also 144. So therefore there's 2 answers, and that's why I say plus or minus 12. A really common incorrect answer is to say 12 squared, because they know 12 squared is 144, but remember that a square root cancels a square, so you should not write the exponents. So another way to show that, by the way, is to say the square root of 144 is the same as the square root of 12 squared, and then the square root and the square cancel out, and all you have left is the 12. Of course, we should remember for these positive roots, square root, fourth root, all those types of things, it can be plus or minus, technically speaking. So it brings us to number 4. What number, if I take 3 of them and multiply them together, is 64? A common incorrect answer for this specific question, by the way, is 8, because they're like, oh, 8 times 8, that's 64. Except I need 3 of them, and 8 times 8 times 8 is not 64, that's 512. So we are looking for 4, because 4 times 4 times 4 is 64. Therefore, the cube root of that says, yeah, take 1 of those, that's my answer, because that's the question, is what number if I were to take 3 of them and multiply them together. It doesn't actually say multiply 3 of them together. That's not the question. So 4 is my answer. And let's move on. Number 5. I know how to number. So number 5 says the square root of 8. Oh yeah, no problem. What number if I take 2 of them and I multiply them together gives me 8? Except there is no number like that, at least not a number that you can think of, and we can see our answer looks a little bit funny. So why is that our answer? Well, because in order to simplify this square root, we're asking ourselves, well, if I were to type this into the calculator, it's not going to be nice. It's going to be like 2.8 something something something, and that's a decimal. That would be the number that if I were to multiply it together by itself or with itself, it would give me 8. But that decimal actually never stops. It never repeats, kind of like pi. So that's a problem. So that means that the strategy we want to use is to find the square root of the part of this number that we can, and then just don't find the square root of the part that we can't, right? So what I mean by that is, well, the square root of 8 is the square root of 4 times 2. Because 4 times 2 is 8. Yeah, no big deal. So if the square root of 8 is the same thing as the square root of 4 times 2, then the square root of 4 is 2. Yeah, square root of 4, that's 2. And then the square root of 2 is, well, that's the part that gives me that decimal answer. That can never simplify. You're never going to be able to get a nice answer out of that because I can't break it down any further, and it's not a nice answer. So where did I get this 2 from? Well, that's the square root of 4. And where did I get this from? That's the part that just couldn't simplify anymore. So that's how I do that problem. Moving on to number 6, it's actually the same exact type of problem. Part of this number is a perfect square and part of this number is not a perfect square. But what to choose? There's so many factors of 175. But let's give it a shot anyways. One thing that you could try, because again, talking strategy here, you could try just dividing by any old thing, right? This is divisible by 5. This is 5 times, what is it, 35? 5 times 35. And then you see, neither one of these are perfect squares. I can't find the square root of 5, and I can't find the square root of 35. I mean, 35 is close to 36, but that's not good enough. Mathematicians don't say, close enough. Or we do, but we call it rounding. But this is not a case where we round. In fact, the reason that we're simplifying here is specifically because I don't want to round. I want an exact answer. So that's not going to work. I don't want that one. And so you might, I tried and it didn't work. But just try something else. No big deal. This also happens to be divisible by 7, and this is 7 times 25. And I actually wrote it in this particular order for a reason. Normally, you're going to write your perfect square first, but that's actually okay, right? It's not a big deal. This is just multiplication, and it can be done in any order. So just like I did in problem 5, I'm going to separate this into 2 problems, 2 roots, I guess I'll say. And one of them is the square root of 7, one of them is the square root of 5. So check it out. Square root of 5, square root of 25. Check it out. That's 5. The square root of 25, I know, and that's where I got the 5 from. I switched the orders of them just because, usually the convention, what mathematicians want you to write it as, they want you to write the whole number part first, then the root. But in their process of getting there, it's not a big deal. You can write it in any order. So there you go. This is 5, and this can't be simplified. If you type into the calculator, it's going to give you an ugly answer. And not only that, it can't be broken down anymore because it's a prime number, and prime numbers that's as far as they go. So this is how I got my answer for number 6. Let's move on to number 7. Number 7 is where we see our first cube root. Nice. All right. So the cube root of 16, we're actually going to use the exact same process, except I don't want to break it down into perfect squares. No, I want perfect cubes because it's a cube root. So I could say that this is like, 4 times 4 or something like that, but that wouldn't help me because 4 is not a perfect cube. It's a perfect square. So this is the exact same idea. You just have to know, is it a perfect square that I'm looking for? Or is it a perfect cube that I'm looking for? And in this case, it's a cube. So what is a perfect cube that goes into this number? How about 8? This is 8 times 2, and not just 8 times 2, it's the cube root of 8 times 2. Big mistake I see from Algebra 1 students is they drop the cube root, they just say, it's 8 times 2. No, it's not. It's the cube root of 8 times 2 because it was the cube root of 16. Don't drop symbols until you've done that particular operation yet, and that's what the cube root is. It's an operation to do. And since we haven't done it yet, it stays. So keep it there. All right, so just like with square root, I can break this into pieces. I can say this is the cube root of 8 and the cube root of 2. And that was an ugly 2, that's okay. Hopefully we can see where I get my answer from. The cube root of 8 is 2 because 2 times 2 times 2 is 8. The cube root of 2, that's a decimal. I don't want to deal with that, so it's just the cube root of 2. And so that's my answer, 2 cube root 2, done. Number 8, again, is the same idea, just with a bigger and scarier number. So you try to divide it by things, and your first several attempts may be unsuccessful. And for instance, you could call this the cube root of 2 times 432. And it's true, 2 times 432 is 864, but 2 is not a perfect cube. 432 is not a perfect cube, so you try something else. You could try dividing it by 3, which it is divisible by 3, but again, you're going to get to the same problem let's try dividing it by 4. So it might take several attempts, but don't give up on it. Just eventually it will work. Or maybe you exhaust every possible number and you realize, actually, I can't break this down into any pairs of perfect squares or cubes or whatever the problem asks for, in which case it actually is as simple as you can get, which would be a nasty trick, and I definitely wouldn't do anything like that on a test or anything like that. Nah. But anyways, this is divisible by 4. This is 4 times 216, which when I say those numbers, one of them should be setting off alarms in your head because 216 is a perfect cube. So sometimes I feel like talking it out slowly can actually hinder your understanding. So I'll say it fast, The cube root of 864 is the same thing as the cube root of 216 times 4. The cube root of 216 is 6. And so my answer is 6 times the cube root of 4. There you go. That's the process that goes on in my head when I'm doing these things. So that's how I get these answers. There's where I get 6 from. That's the cube root of 4, which, as you see, is also part of my answer. Done. Number 9. And in fact, this whole section, all on fractional exponents. Let me scroll down just a little bit. There we go. Fractional exponents, and these can sound scary. Oh joy, it's everybody's favorite things, fractions. Inside of exponents, even better. But it's just a simple definition. This is just the square root of 9. So a fractional exponent simply says the denominator of that fraction is what type of root it is. And since this is a denominator of 2, this is a square root. It also says that the numerator it remains as a power, but things to the power of 1 are themselves. They don't change. So this is just the square root of 9, and that is plus or minus 3. So nice. Moving on to number 10, again, the denominator is the root, so this is a cube root instead of a square root, and that means that this is how I got my answer of 5. The cube root of 125, because 5 times 5 times 5, there's 3 of them, is 125. So that's how I got 5. Number 11 says to the power of 3 over 2. This is where we're going to get a little bit more technical, but not too much. We're using exactly the same definition. The denominator is 2, so this is going to be a square root. Feel free to put in a little 2 there if you want to remind yourself where the 2 goes, but you don't need it. And then the numerator stays as an exponent. So there we go. We can do this in 2 pieces. The square root of 49, that is plus or minus 7, which, by the way, is why I put plus or minus. If there's a worksheet that we did this type of stuff where sometimes I would omit the plus or minus, but since we did a square root, well, square roots can have 2 answers, and so I really should put plus or minus, and then to the power of 3. So this is going to be 7 to the power of 3, and again, if I want to be fancy, I can say plus or minus 7 to the power of 3, and if it was positive, 7 times 7 times 7, that's positive 343. And if it was negative, then negative 7 times negative 7 times negative 7 is negative 343. So that's how I got those answers. Brings us to number 12. This one we see is not plus or minus because these are both odd powers. In fact, the root here is odd. So therefore, this is going to be the cube root of 27 raised to the power of 5. The cube root of 27 is 3, not plus or minus 3, just 3. And then 3 to the power of 5. This is 3 times 3 times 3 times 3 times 3. And that's 243. So that's what I got for my answer. And hopefully that makes some sense, all right? And we're back starting on number 13. We have 7x to the power of 0, y, and a common misconception here is if you see a power of 0, that means the answer is 1. But no, just this part simplifies to 1. X to the power of 0, whoops, x to the power of 0 simplifies to 1, so this becomes 7 times 1 times y. Another way to look at it is y has its own exponent. It's next to x, but it doesn't share exponents unless there was like parentheses or something like that. Yeah, it's not happening here. So this is 7 to the power of 1. This is y to the power of 1. and anything to the power of 1 is itself, so that's where I got the 7 and the y. So sure, 7 times 1 times y is 7y. Well, that's it. Number 14, a really, really common mistake here would be to say that this is 36 to some power, or would be to say that this is 6 to the power of 4, because there's 3 6's and I'm multiplying by another one, right? Except no, I'm not multiplying by another one. 6 to the power of 0 is really 1, just like x to the power of 0 was 1. So this is really 6 to the power of 3 times 1. And I know 6 to the power of 3, and that's 216, easy. And that's how I got my answer. Moving on to number 15, x squared times x. Again, so many common mistakes here. One common mistake is to call it 2x squared. That's wrong, don't do that. Another common mistake is just to say x squared, because you add the exponents, right? 2 plus no exponent is 2. But that's wrong too, because again, x does have an exponent, and if you can't see an exponent, it's 1. So this is really x to the power of 2 plus 1, and that's where I got 3. Moving on to number 16, again, this is the type of problem that causes so many simple mistakes. You see a to the power of 4 and b to the power of 2, and you want to say, I'm multiplying. I'm going to add these exponents. And so I'll see answers like ab to the power of 6, or maybe a to the power of 6, or just b to the power of 6, or something like that. And all variations of that is wrong. Don't do that. It's not correct. And this is because, well, a to the 4th means this, a times a times a times a. B squared means b times b, and those just aren't the same thing. I can't say ab to the 6th. That would say 1a and 6 b's. That's just not what I have here. So the best that I can do is remove the little multiplication symbol, because writing things next to each other means to multiply them anyways. So this is actually the best that I can do. There's 4 a's and there's 2 b's, and that's it. So that's how I would simplify this problem. Just remove the multiplication symbol, because I don't need it to say multiplying. I can just put them next to each other. Moving on, number 17. This is where things get a little bit spicy. We have quite an ugly looking, I'll just say it. It's ugly looking expression, but we can break things down into parts. If we have a lot going on, then just look at one piece at a time. This is 3 times 6. Where did I get those from? Well, there's 3, there's 6, and everything's being multiplied. Everything's being multiplied, even the stuff that doesn't have a multiplication symbol in between it. Well, I just said in the previous problem, just because there's no multiplication symbol doesn't mean they're not multiplying. Just writing things next to each other means to multiply. So this is 3 times f to the 4th times g times 6 times f squared times g squared. Everything's being multiplied. So I can rewrite it in whatever order I want. 3 times 6 is 18. I have f to the 4th times f squared, which, as we saw in a previous problem, which one was that? Number 15, I think. We can add those exponents. So this is f to the power of 4 plus 2. There we go. That's a 2. It's not a z. And that's where I got 6 from. Same deal with g. This is g times g squared. And that's like exactly what I had in 15, just with g instead of x. And so this is g to the power of 1 plus 2. And that's where I got 3. All right. So that's 17. And I just do each piece, and then you put it all together, and that's your answer. Number 18. Yeah, these problems are getting so long I had to drop it down. But again, same idea. -4 times 2. This time the problem has 2 multiplication symbols in there, but really, again, everything's being multiplied. There's a multiplication here and there and there and here and here and here. All of these in between every single factor, all of them have multiplications that we just don't bother writing. So I can take that -4 and that 2, just do those, and this is, I guess I should get rid of that equal sign. Let's try that again. -4 times 2. This is -8. Hey, look, that's how I got that. The a's, I have an a, I have an a to the 5th, and I have, that's it. So a times a to the 5th is a to the 1 plus 5. B's are up next. I have 1b, 2b's, 3b's. I could use the exponent properties here, or I could just say, actually, that's just a definition. Something being multiplied by itself 3 times is b to the power of 3. But I could say that those all have an exponent of 1, and 1 plus 1 plus 1 is 3. Yeah, so there's multiple ways of approaching this part of the problem. C's, I have 3 C's and I have 2 C's, which means I have c to the power of 3 plus 2, and that's 5. And that's where I got c to the power of 5. Easy. So as you can see, I'm going to get a little lecture-y here in the last little part here. The calculations are easy. It's like 1 plus 2, 3 plus 2, 1 plus 5. Like the calculations are super easy. You just have to know what property, what the rule is that says that you should be adding these or you should be multiplying those, right? And that's it. If you know what the directions, what the property is telling you to do, then the actual calculation is just child's play. Anyways, I digress. Number 19. This time we see our first problem with a fraction. And is it our first problem? One of our first problems. Maybe it is. And again, I'm going to approach it in exactly the same way. I'm going to take 16 over 12. I'm going to break that down. The best number to divide these by is 4, but that's not the only thing that I could do. If you saw that these were both even, yes, you could do this in multiple steps. You could say that this is 8 over 6, and then divide again, because they're still both even, and you should get 4 over 3, which is exactly what I had right there. For the x's, this is x over x squared, right? Which, again, you can use the property, the rule that says you can subtract the exponents, or you can do what I think is playing it a little bit more safely and actually write it out. This is 1x divided by 2 x's. Then I can say, well, I have one multiplying factor and one dividing factor that cancel out, and that gets me 1 over x, and that's why I have 1x on the denominator. Or I guess it's 3x, but you know what I mean, x to the power of 1, that's what I should call it, and it's on the denominator. Same deal with y's. I have y to the 5th over y squared. This is 5 y's all being multiplied together, and they're being divided by 2 more y's. And so just like I did with the x's, cancel, 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 cancel. I have 3 y's left over. All 3 of them are on the numerator, and that's where I get y to the power of 3 on the numerator from, and that's it. So I'm going to scroll down a little bit more so we can take a look at number 20. And we see our answer, and this one is more complicated. There's just more stuff going on. It's even in 2 separate fractions, which can seem scary, except just like with the multiplication, I can kind of just ignore that that's happening and grab whatever pieces that I want and put it together. Like this. This is a negative 10 times a negative 2, sure. Those are on my numerator, and on my denominator, I have a 2 and a 4. Okay, sure. A negative times a negative is a positive. So this is going to be 20, positive 20, and 2 times 4 is 8. I've already shown you that you can do this in multiple steps, like the divide by 2 again, but these are divisible by 4, and so I'm going to divide both numbers by 4. I get 5, and I get 2. That's where I get 5 over 2. I can look at the a's next. I have a to the 3rd, and I have another a on the numerator. There's a to the 3rd and another a. I have one more a on the denominator, and this is another one where I can write it out. This would be a times a times a times another a, and then divide by a on the bottom. And I could do that whole cancel, cancel thing. But this one, I actually notice that I can do a little trick here. So if you're looking to save some time or mental power or whatever, you could say, well, I don't have to write this one out because these ones cancel immediately. A over a cancel, and I'm left with a to the 3rd on the numerator. And that's why I have a to the 3rd on the numerator of my final answer. Okay, cool. And that leaves the b's. I have 2 b's on the numerator. I have a b and a b to the third on the denominator. Cool. I'll go ahead and write this one out. This will be b times b, and here's b times b times b times b. So there's 4 b's on the denominator. And like I've done so with the previous problem, I'm going to cancel, and again, and I end up with 2 b's on the denominator, and that means my answer key has a mistake, although the answer key that you will see will be fixed. And so, yeah, totally, it says squared there, and it did the whole time. All right, cool. So that is why I have b squared on my denominator. All right, cool, easy. Yeah, that's correct. I was just making sure I didn't actually get it right the first time and make a mistake here. All right, so that moves on, or we can move on to the final problem. So let me scroll down one more time. That'll be fine. And number 21, we have our first problem that has parentheses in it, which means we're going to be using our, this one's actually technically called the power of products, not to be confused with the product of powers. Whatever. Basically, it's the one that's don't actually call it this. It's the, the distributive property of exponents. You didn't hear it from me. It's not actually called that, all right? But we can do this. Say this is going to be 6 to the power of 3, m to the 4th to the power of 3, and then n to the power of 3. So every single thing in that, in those parentheses, every single factor gets its own power of 3. So this will be 6 to the power of 3, which is how I got 216. This is m to the 4th to the power of 3. And that's where we have to use the power of powers property. When you distribute into something that already has a power, I called it distribute. Okay, don't make fun of me. Then you multiply the powers, and that's where I got m to the power of 12. Easy. And then n also gets that power of 3, and so that's where I got all those numbers. Number 22, we're going to do exactly the same thing. This time, however, there's so much more to distribute into. We have 3 factors on the numerator and 2 on the denominator, and each one of them is going to get that power of -2. So this will be 3 to the power of -2, x to the power of -2, y to the power of -4, 2 to the power of -2, and x to the power of -8. So this one is a bit more complicated, but you know what? We can still handle it. We have negative exponents, and our last lesson, I should say, was on how to deal with negative exponents, and it has nothing to do with negative numbers. All it means is that anything that has a negative exponent wants to go to the other side of the fraction. So if it was on the numerator, it wants to go to the denominator, and vice versa. If it was on the denominator, it wants to be on the numerator. So we're going to rewrite this fraction, but flip everything over to eliminate those negative exponents. So this will be 2 to the power of, not 4, I was getting ahead of myself, 2 to the power of 2, x to the power of 8, 3 to the power of 2, x squared, y to the 4th. And hopefully we see where we get these answers from. 2 squared is 4, 3 squared is 9. I have 8 x's on the numerator and 2 on the denominator, and 8 minus 2 is 6. And then finally, the only y that I have is this y to the 4th, and so that's where I got y to the 4th, no big deal. Number 23, we have, I guess, a simpler problem. Maybe we should have switched those. Yeah, whatever. And let's see what we can do. Sorry, I'm tripping over my words here. So we can take our numbers, our coefficients, and look at just them, 2 over 5. Is there anything that can simplify those? No, those are both prime numbers. No prime numbers have anything in common except for 1, and 1 is not how you break numbers down. So that's it. Next we have x's. We have x to the -3 over x, which means we can actually flip the -3 down to the bottom, and it becomes +3. And I have 1, and I have, now it's not very good power. Let me try that again. I have 1x, and I have 3 more x's. That's where I get 4 of them. And They are on the denominator, by the way. And we have y on the denominator with a power of -1. We're going to flip it up to the numerator. And we could call it y to the power of 1, but that's just not what you do. You don't say power of 1 if you can avoid it, which you can because you're the one writing it. Duh. So we would just say y over 1, and that's where we get y on the numerator. So 2 on the numerator, y on the numerator, 5 on the denominator, and 4 x's on the denominator. That's how I got my answer. And that leaves us, last but not least, with number 24. Once again, we see 3 different factors here, actually 3 factors. 2 of them aren't different, that's okay. We're going to distribute, again, don't actually call it that. We're going to give everything inside the parentheses the outside power. So this will be 2 to the power of -2, n to the power of -5 times -2, and n to the power of 2 times -2. Okay, so that's what we got. And let's do some simplifications. I'll leave this as, not a fraction yet, because I want to do a little bit of simplifying before I turn it into a fraction. -5 times -2 is 10, positive 10. 2 times -2 is -4. And so check it out. I have 10, and because I'm multiplying the same base here, I can add -4. So this is going to be 10 plus -4, which is just 10 minus 4. And so that's where I get 6 from. That's n to the power of 6. So I can rewrite this again, call it 2 to the power of -2 times n to the 6th. Awesome. And then this is where I'm going to say, all right, that's a negative exponent. And so I can flip that down to the bottom of the fraction, because remember, everything's a fraction. It's just over 1. And 2 squared is 4. So that's where I get 4 from. There you go. So that is all of the problems from this practice test done in like 30-something minutes. And that's what you're going to be expected to know. And so if any of this stuff did seem complicated, or you weren't sure how to solve it and you had to resort to watching this video, no big deal. But you should go back and check the videos and the example problems that we did previously and get some practice on that. Another good resource is to check out Khan Academy, which I'll probably assign to you anyways. So good luck. Hopefully it made sense. Thank you for watching, and I will see you again next time. Bye-bye.